All right, so yesterday we started off with our introduction to substitution reactions, and we said that they always involve a nucleophile replacing a leaving group, but there's two different mechanisms through which they can occur. We said option one was where that leaving group falls off first, you form a carbocation, and then your nucleophile attacks in. And just like with the quiz, we said we could have a reaction coordinate diagram describing this, where the first hump you have to overcome is really, really large. You're forming a very unstable intermediate that's high in energy, so that activation energy, the first activation energy, is going to be a very large barrier. Going from the carbocation intermediate to the product, it's a pretty low hump, so that's not going to be your rate determining step. The rate determining step for this reaction is going to involve your leaving group falling off, and we can describe this with a rate equation. So pretty straightforward. Option two is more like what we saw in the quiz, where the nucleophile will attack the carbon, that's the electrophile, and shove off that leaving group. When you do this, it's bimolecular, and the nucleophilic attack of that carbon is now rate limiting, and you can describe the rate equation as we saw yesterday. Like I said, both in class and like you guys determined on the quiz, if you double the nucleophile concentration and the rate doubles, then the reaction's SN2. If the rate is unchanged, then that's likely a clue that it's SN1. So you can use simple rate experiments to deduce what sort of mechanism is more likely. Let's talk about electrophiles today, though. So let's take a look at the SN1 reaction first. Oops, sorry, I'll unplug that. So in the SN1 reaction, let's compare two reactions. So compare the following. The first reaction is going to look like this, where we've got a leaving group and we've got a nucleophile. And I want you guys to complete this reaction as if it were an SN1 reaction. And then for option B, I'm going to have another example. Looks pretty similar, where our leaving group is now attached to a tertiary carbon. And again, I want you to complete this as an SN1 reaction. So try drawing all of the arrow pushing and any intermediates in order to complete both of these reactions. And then once you're done with that, try to check with your neighbor.
Did you say we're doing both as SN1s?
Yep, both as SN1 reactions. We're just going to do a simple comparison. Give me a thumbs up if you think you got it, too. See a couple thumbs? I'll give you guys a hint, too. What's the first step in an SN1 reaction? Leaving group falling off, right? So I'll get you guys started with the first arrow. Now we need to draw our intermediates that result. Thumbs up if you got it. All right, now what I want you guys to do is to check with your neighbor and see which one's more likely to occur, reaction A or reaction B, and then discuss. All right, do we have agreement on which one's going to be fastest? Or more likely, I should say? B? Does anybody want to explain why they think B is going to be the more likely reaction? What do you think, Andy?
Because when the leaving group comes off, it'll make a tertiary carbocation as opposed to a primary one.
Exactly. So let's take a look at this. In option B, we're forming a tertiary carbocation. Last week we said tertiary carbocations are a heck of a lot more stable than primary carbocations. This is a primary carbocation. We said the likelihood of seeing a primary carbocation is pretty dang small. And let's make a note of this. Reaction B is much more likely to undergo a SN1 reaction since you form a more stable intermediate. And this is in general true with all SN1 reactions. So with an SN1 reaction, a tertiary carbocation is going to be more favorable than a secondary, which is going to be more favorable than a primary, which is going to be more stable than a methyl carbocation, right? So increasing carbocation stability. And I'm going to put an asterisk there. Why do you think I'm going to put an asterisk there? Because it's OChem and there's always an exception that drives people nuts, right? So we'll talk about that in a second, but this same trend follows along with increasing likelihood of an SN1 reaction. Oop. So that's pretty simple. Now we got to go back to that asterisk. I'll go, but what about this carbocation where we've got carbocation that's on a primary carbon and we've got a benzene ring right next door? Because resonance. You guys are beginning to see that this is a trend, right? So in this case, it's a primary carbocation, but it's super duper stable because you can delocalize that positive charge all the way through that adjacent ring, right? So in this case, we can say this is very stable due to resonance. Resonance is kind of our trump card when it comes to the stability of carbocations, right? It's in fact more stable than a tertiary carbocation if you have resonance. All right, there's another common example too that we have to consider. And the second example looks like this. Same thing is true. This one has resonance. Even though it's a primary carbon, you can take this pi bond, move it over, and delocalize it across both carbons. So we'll make a note that both of these have resonance. Does anybody remember what that bottom one's called? Close. It's an allylic carbocation. Did you have a question, Marcus?
Yeah, in terms of stability between those two, though, the benzene is going to be much more stable because there's more resonance, right? And that ring structure is extremely stable because of the hybridization.
That's a good question. So Marcus was asking what's more stable, the benzene example where the carbocation's on that carbon next door or the allylic carbocation below it. They're both really stable. It'd be hard to say which one's necessarily more stable in that case. So let's call these by their true names. This is our allylic carbocation. You might see these pop up. The top one's called benzylic. So make sure that you always remember to check for resonance when you're assessing the stability of carbocations. Does that make sense? All right. Now we've got another thing to consider, and that's stereochemistry. So in chapter 5, we talked a lot about stereochemistry, the handedness of molecules. This comes back again when we talk about stereochemistry. So let's consider option number 1 here. Okay. And option number 1, I'm going to do an SN1 reaction. And first thing I want you guys to do is to name our starting material. And then we have to complete the reaction using arrow pushing. So what would this starting material be called? All right, let's do this as a class. This one's a little tricky. What's our longest parent chain? A pentane. Should I number it going left to right or right to left?
Right to left.
Ah, right to left. In this case, can you see how the first substituent comes off carbon 2 if we go right to left? And then we've got 3, 4, 5. So we know we've got a pentane. And then we have to determine whether or not it's R or S. Okay? So I know our iodine is going to be position 1. It's the heaviest. What will be position 2? Will it be the isopropyl group, the ethyl group, or the methyl group? Isopropyl. Okay, that means our ethyl will be last. So we're going around counterclockwise. So now we need to piece this together. Is it going to be R or S? R, like a pirate. So it's going to be R. And in this case, it's going to be 3 iodo. 2, 3 dimethyl pentane. So that's good review for nomenclature. Now what we need to do is do an SN1 reaction and complete it. But this time, let's just stop at the intermediates.
Can I ask a question?
Yeah.
When we're labeling stereocenters, do we need to label which of the carbons that's coming off of, like 3R, or is that only when there's multiple stereocenters in one?
That's a good question. So Grace was asking, if you have a stereocenter, do you need to list which carbon it comes off of? In general, it's a good idea if you have more than one stereocenter, but if you have only one, it's assumed to be at wherever the stereocenter is. So if we go on with this SN1 reaction, the first step is what again? The iodide falling off. Okay, so I'm going to draw that with our red arrow. Now we have to think about the intermediate. It's a carbocation, right? Carbocations are probably what shape, according to Vesper theory? So let's think about it, right? We've got a methyl group, we've got an ethyl group, and we've got an isopropyl group with a positive charge. Trigonal planar, right? So what I'm going to do to represent this a little bit better is do a side-on view. Okay. So in this case, I'm going to have my central carbon. I'm going to keep my isopropyl here. The ethyl group is now going to be going kind of to the back. And over here, I'll have my methyl group. If we think about the carbocation, we have an orbital that we need to consider, right? What orbital? Big old p orbital. So this p orbital is sticking up and down. It's got a positive charge. In this process, this iodide is just kind of hanging out down here. It just fell off of that carbon. Okay. Now if we think about our chlorine, or our chloride, it's going to be our nucleophile. Question is, which side of the carbon will it attack? and why? Or will it attack both sides? What do you think, Kelsey?
I think it's going to attack where the iodine is.
It could, absolutely. So if we think about it, we could attack this lobe, right? That lobe's empty. So we could do a bottom attack. Could it attack the top lobe too? Yeah, it's an either or situation, right? If we think about that p orbital, it's on both sides. It's equally likely that it could attack from the top or bottom face, more or less. So it could attack from the top or the bottom. So let's consider the products that would come out of this. So I'll do a top side attack, and I'll do a bottom side attack. In the top side attack, we've got our chlorine now attached here. Our isopropyl group's kind of folded down. Our methyl group's there. And now our ethyl group's kind of sticking in the back, right? Can you guys see how that chlorine is now attached at that top lobe? Okay. Now let's take a look at what it would look like if it attacks from the bottom lobe. Well, let me clean this up a bit. All right, so now an even more abstract question. Do you think the bottom face attack is going to be more likely or the top face attack? The top side? Why do you think that, Grace?
Well, because the iodine maybe isn't that far away, or it's in that area.
Yeah, exactly. If we think about this, she was saying that this iodine is kind of crowding that orbital a little bit. It just fell off of that side. It's occupying a little bit of that space. That means that the bottom side attack is a little bit less likely, but it still occurs. So let's make a note of that. So a little less likely. But still occurs. And that really has to do with the blocking ability of that iodine. All right, if we look at the top one, is that going to be R or S? What do you guys think? This stereo center right here? What do you guys think? So highest priority would be up here, second highest, third highest. Sorry, that's a little sloppy. If we go around, that's clockwise. However, our lowest priority is coming towards us. So it will most likely be an S, or it is an S, I should say. So in this top example, we could say, all right, we might get this S, stereochemistry, coming out. What's the bottom one?
R.
R. What's the relationship between these two? Ah. So are they mirror images of one another? I don't know. I'd say so. If we look down here, can you see how the methyl groups are mirrored? We've got an ethyl group that's mirrored, an isopropyl group that's mirrored, and the chlorines are on opposite sides. So I would say that they're mirror images. Another clue we said when we were looking at pairs of enantiomers is that all of the stereochemistry is flipped. In this case, we flipped all of our stereochemistry from S to R. So when you do an SN1 reaction, it's very common that you get a mixture of enantiomers out of it. What happens if we get a 50-50 mixture? What do we call that? Racemic. Some SN1 reactions will give you close to a racemic mixture. All right, so let's make some notes. SN1 reactions result in a mixture of enantiomers. With a slight preference towards retention of stereochemistry.
Does that mean there's a slight preference for that one to stay as an R as opposed to an S?
That's a good question. So what do I mean by retention of stereochemistry? It's not an absolute retention in that R always stays as R, S always stays as S. What it means is that that position that the iodide fell off of gets replaced by the nucleophile. That just means retention.
Isn't it retention against that then? Because we said the S was more stable.
In this case, what do you think is more stable, the S enantiomer or the R enantiomer? Or do you think they're equally stable?
If they're equally stable, it's more likely to occur, is what I meant.
That's a good question. So you're asking, because the S one's more likely to occur, it is more likely to occur, but that doesn't necessarily mean that it's more stable. It just has to do with the blocking effect of that iodine. Enantiomers have the exact same physical properties. All right, now we've done a good job of analyzing our SN1 reactions, but what I want to do is go back and look at our SN2 reactions a little bit. So I'm going to go back and look at electrophiles with SN2. Sorry to change back on you guys. But let's take a look at SN2 electrophiles, and then we'll go and look at SN2 stereochemistry. Okay, with SN2 reactions, let's do the same thing that we did before. We'll do compare the following. In this case, we're looking at the electrophilic role within the reaction. So yeah, you could put SN2 reactions or SN2 electrophiles. Just like we did in the first example, we'll say, all right, we've got a leaving group. We've got a nucleophile that's got a negative charge. Or we've got option B, where we've got a leaving group and we've got a nucleophile over here. Let's complete this reaction using arrow pushing. And then what I want you guys to do is to draw the products out and then ask your neighbor, which one do you think is more likely for an SN2 reaction, option A or option B? So I'll give you guys a minute to work on that. Let's see a thumbs up if you feel confident with your reaction mechanism. All right, so now let's try to discuss with the neighbor and problem solve which one's more likely.
Yeah, because either way, there's no carbon
Oh.
Yeah.
I mean,
There are
SN2.
SN2, there are.
Yeah, that's right. SN2.
That form of you. I feel like there should be a, I know, but
So this guy would be
the blocking you're saying goes where it's hard to get in there. Maybe it's not too right, but I still feel there's more mixture.
Especially since those are different types. I mean, looking at like that would be I feel like there's less of a preference than I feel like there's to be a slight preference.
Well, S1 doesn't or doesn't do the top one.
All right, give me a thumbs up if you and your neighbor agree. Few thumbs. Some debate still. All right, does anybody want to share their opinion on which one they think is more likely to occur? What do you think? Okay, so Kelsey was saying she thinks reaction A is more likely because that nucleophile has an easier time running into that carbon. Is that right? Okay, I agree with you. If you think about option B, that nucleophile has to squeeze into a pretty tight spot before it can run into that carbon, right? What do we call that when you've got a bunch of bulk? Sterics, right? So option B, we've got this entire backside which is sterically bulky. And that means it's going to make it hard for that nucleophile to actually reach that carbon. It's going to make it much less likely. So we'll put a little note that this is not likely. In this case, are we concerned with carbocation stability? No, it doesn't go through a carbocation at all, so it doesn't really matter. So let's make a note of this. This is very different than with SN1 reactions. We aren't concerned with intermediates at all. All we're concerned about is with the ability to attack that electrophile. So SN2 reactions are more favorable if the backside, it's a scientific term, of the electrophile is more accessible. Okay, so we can kind of block this off as our common theme for SN2. And just like with SN1, we could say, all right, well, now we can kind of classify our electrophile as a primary, secondary, tertiary. So let's do that again. So I've got tertiary here. We know that in general, we've got secondary, primary, and methyl. We know that in general, these have increasing amount of backside exposure, so to speak. Just one second. And that also means that as we get towards methyl electrophiles, they become much more reactive towards an SN2 reaction. That also means we have increasing likelihood for SN2. Does that make sense? We're always concerned with the approachability of that backside. All right, just like we did with SN1, now we have to go back and we have to look at stereochemistry. So with SN1 reactions, we said that we get a mixture of enantiomers. Now we need to look at this more closely with option 2. And that's our SN2 reaction. Oop. All right, with an SN2 reaction, let's take an example, just like we did before. And this time I'm going to look at the transition state. What is a transition state again?
Bonds are broken and formed.
Broken and formed, right? It's different than an intermediate. We can't isolate a transition state. We can isolate an intermediate. So in example A, I'm going to have an ethyl group here attached to a carbon with a bromine. Then we've got a methyl group in the back and a hydrogen right here. So in this case, is this electrophile primary, secondary, or tertiary? Secondary. The carbon's attached to 2 other carbons, so it's going to be secondary. This is kind of an in-between case, but maybe it will do SN2. And in this case, let's draw our nucleophile as just a generic Nu-. And let's say I do a front side attack, and we kick off our bromine. Let's draw that transition state. So in this case, our ethyl group would be down here. Our carbon would be here. We'd still have this hydrogen kind of sticking out as a wedge. We'd have our methyl group back here. The bromine would be falling off, so I'll draw that as a dashed line. And our nucleophile would be approaching. And I like to bracket these and include a double dagger to indicate that this is absolutely a transition state. It's not something we can get a bottle of. In this case, our nucleophile is delta negative. Our bromine is halfway falling off, so that's negative. And our central carbon is partial positive. Let's compare this to our example B. And in example B, we're going to do the same reaction. However, this time we're going to do a backside attack. So we've got our nucleophile here with the negative charge. This time it's going to sneak around all the way to the backside and then shove off that bromine. So now we've got Nu here. Got this hydrogen that's still a wedge, this methyl group that's still a dash, ethyl group still a line. However, our bromine's falling off the opposite side. Again, this is a double dagger. Let me change this arrow a little bit, sorry if that ruins your notes. And then let's fill in our partial negatives and positives again. So we've got partial negative on our bromine, partial negative on our nucleophile, and partial positive on our carbon. We already talked about the backside attack, but now let's try to rationalize why it occurs. What do you guys think? Why is the backside attack, that option B, more likely if we look at the transition state? Does anybody, what do you think, Marcus?
If you're coming in from the front, that group is leaving the same direction that the nucleophile is coming in from, so it'd be easier to come in from the back, so it's coming in the back as the other one's falling off because it's a rapid transition.
Yeah, if we think about this, you're right. If this bromine's attacking in right here, it's got its own electron cloud that's partial negative. It doesn't want to be next to another electron cloud that's also partial negative, right? That's repulsive. If we think about VSEPR theory, we want to distribute electron density as far away from each other as possible. So option B makes a lot more sense in terms of VSEPR theory. We want to keep those groups as far apart from one another as possible. All right, so let's draw our products out that we would get. So for this bottom one, we've got a nucleophile that added in, our hydrogen's still a wedge, our methyl group's still a dash, and our ethyl group's down here. What we call this is a inversion of stereochemistry. All right, if we had the top example, it would look similar. However, it'd be a mirror image. Oh, shoot. Here we go. I can do it. Nu, Et, got our hydrogen, and we've got our methyl group. This would be a retention of stereochemistry. Meaning that nucleophile occupies the position that the leaving group was once in. Do you think we're going to get a mixture of both of these? In this case, I'd say it's very, very unlikely that you're going to see any retention of stereochemistry. In fact, if you check this experimentally, you get 0% retention. So the top one's going to be not observed. Did you have a question, Grace? Or did somebody over here do? No, okay. All right, so SN2 reactions always have this inversion of stereochemistry. Let's take a look at example B that we know is more accurate when describing the stereochemistry. What's the geometry of our transition state? Yeah, exactly. One of the goofy shapes. This one's a trigonal, bipyramidal transition state. This is exactly what occurs. And just like I was saying before, does that automatically mean we switch from R to S? What's the stereochemistry of our product? Can we assign R or S to it? We don't know the nucleophile, right? So we can't necessarily say that it always switches from R to S. It depends on the identity of the nucleophile. However, we always know that it will flip inside out due to that backside attack. The analogy I like using is if you've ever been outside on a windy day with an umbrella, your umbrella can flip inside out. That's an inversion of stereochemistry at that central point on your umbrella. Same thing happens here. All right, so let's take a look at a nice video that I think does a good job of explaining the stereochemistry. And you'll have to excuse this cheesy animation.
Primary halogenoalkanes undergo SN2 reactions, where the S denotes a substitution reaction. The N shows the reaction involves a nucleophile. 2 is the number of species involved in the slowest rate-determining step. A nucleophile is an electron pair donor. It is attracted towards species carrying a full or partial positive charge, with which it can form a dative covalent bond. Consider the reaction between a hydroxide ion in solution and bromoethane. Both reactants are involved in determining the rate of the reaction in a one-step process. The hydroxide ion attacks the carbon atom from the opposite side to the halogen atom. Because the bromine atom, A, is so large it impedes the approach of the smaller hydroxide ion, and B, it repels the negative charge nucleophile. The lone electron pair on the nucleophile forms a new dative covalent bond with the partially charged carbon atom to give an unstable transition state complex. The complex behaves like an umbrella blown inside out as the bonds rearrange into a tetrahedral structure. The bromide ion, called the leaving group, is released.
You guys want to see the SN1 one?
Yeah.
All right. Let's take a look at SN1 now.
Tertiary halogenoalkanes undergo SN1 reactions, where S indicates a substitution reaction is occurring, N indicates that a nucleophile is involved, and 1 indicates that only one species is involved in the slowest rate-determining step. In tertiary halogenoalkanes, the small hydrogen atoms in primary halogenoalkanes are replaced by bulkier alkyl groups. The bulky alkyl groups do not allow attacking species to approach the central carbon atom. Consider the reaction between 2-methyl 2-bromopropane and a hydroxide ion. It has a two-step enthalpy profile. The first step, the heterolytic fission of the carbon-bromine bond, has a high activation energy, EA1, and therefore determines the rate of the reaction. The first step involves only the halogenoalkane and proceeds via a transition state complex to form a carbocation. The second step has a much lower activation energy, EA2, and hence is considerably faster than the first step. The carbocation reacts with the nucleophilic hydroxide ion via a second transition state to form the product 2-methyl-propan-2-ol. Transition state. Carbocation. EA2.
There we go. Hopefully that clarifies it a bit. I know when I took OChem, I think I've told a lot of you this, but I was three-dimensionally challenged. So oftentimes having a model kit can help you see those transition states or those intermediates a little bit more clearly. All right, last thing I want to do before we head out today is hopefully you guys all grabbed a substitution overview handout. I really like doing this for this chapter because it can help separate everything into a nice organized table. So if we think about SN1 versus SN2, we can start filling in these boxes a little bit. We already know the variables and a couple of them at least. So let's do the first part. The mechanism for SN2, is it concerted or stepwise? Concerted. That means it's a one-step reaction versus SN1, which is stepwise. All right, that means that the nucleophile shoves off our leaving group in one step versus stepwise where the leaving group falls off first. All right, rate equation for SN2. What would the rate equation be? So rate equals little k. And do we have both nucleophile and electrophile? Yes. So I'll just do Nu and E. And rate for SN1. Do we include the nucleophile? No, just the electrophile. So in this case, it's the thing with your leaving group attached. Stereochemistry, we said SN2 does what again? Does it form a mixture? Does it invert things? Does it retain stereochemistry? What happens with SN2? Inversion. What about SN1? You get a mixture of enantiomers. Some people will call that a scrambling of stereochemistry. You get a mixture of two different stereoisomers out of it. All right, if we think about our substrate, meaning our electrophile, if we have SN2, what works best? Is it methyl, primary, secondary, tertiary? For SN2? Methyl. Remember SN2, we want the more exposed backside. So we'll say methyl is better than primary, which is better than secondary, which is better than tertiary. And this is because sterics influence our rate. We need to have an exposed backside. SN1 we know is opposite. We said that tertiary is actually better than secondary, which is better than primary, which is better than methyl, with the exceptions when you have resonance, right? And in this case, we said that carbocation stability influences rate. All right, tomorrow when we come back, we're going to talk about the nucleophile, the leaving group, and the solvent in a lot more detail. But my goal is to kind of piece this together in a way where things feel fairly intuitive, because a lot of these themes will show up again in Chapter 8. Chapter 8, we need to know about nucleophiles versus bases and things like that. So we're going to cover that in a lot more detail tomorrow.